This is the Monkey Induction speaker. What it is an audio amplifier. You can see I've taken this one apart a little bit. It's kind of interesting. The idea is you have a cell phone, and of course cell phones are pretty small speakers, so they don't really create a strong audio output. But if you start playing, and you put it next to the speaker. Let's just unroll the foils here, and let's over to another photograph. And of course, it's amplifying. But it's not just picking up the audio signal, it's actually picking up the electromagnetic signal of the phone. Some of the speakers here, you're probably getting a magnetic field from the coil windings, and it's picking that up and amplifying, which is kind of neat. And if you take it apart, you can see there's a couple transformers here, so I think it's picking up the signal somehow, and then of course amplifying. Let's analyze the circuitry. So I have a little speaker here, probably of course a bit larger than a cell phone, but same idea. It probably traces a magnetic field that I presume what's happening is picking up by these two transformers. I suspect this is a stereo pickup. It's only a monophonic device. There's only a single speaker here, but the cell phone actually has two speakers, and they're kind of in this position. So to test that theory out, I have a signal generator. I'll just turn that on. If I move the speaker close to the transformer, it'll start to amplify, as you'd expect. If I move over to the other transformer, much the same. Which kind of proves there's probably a stereo pickup going on here. We're trying to pick up the signals from both the speakers on the cell phone. Like, i.e., it's not a difference between the fields, but it's actually each one's picking up individually. So here's the inductive pickup, and I've sketched out the very simple schematic. You can see that they've shorted the windings on the transformers, and they connect them essentially in series, and I presume the windings are such that any induced voltage in any one coil always reinforces itself. And basically, if you have a magnetic field crossing over these windings, it'll induce a voltage, and of course that can be picked up by the circuit. So going to the main circuit board, the amplifier is a MD8403. It's a Class D amplifier from the Shenzhen Megapower Integrated Corporation. I think it's a knockoff of something from Diodes Incorporated. They have a very similar part number, but I suspect this is a clone, given that the provenance of this. I got it out of a dollar store, this amplifier, for $2. So up here, a voltage regulator, the AMS 51117. That's just a simple 3-terminal regulator, probably not too interesting to decap. And then a lithium-ion battery charger, because interestingly enough, when they designed this, they actually designed it with what looks like a typical cell phone battery. And if you don't want to use a lithium-ion battery, or maybe if they sold it in a different version, there was one variation where you could put some AA batteries in as well. So certainly quite a curious design. Let's de-encapsulate at least the amplifier. I suspect that's kind of interesting. A Class D amplifier works by switching a couple MOSFETs on at fairly high speed and filtering the output. So the structure might be kind of interesting to look at. Okay, so this is the Class D amplifier chip. I've removed the packaging, and what we're looking at is the actual silicon die. If we pop back to the Wikipedia article on Class D amplifiers, you can see their main attribute is the concept of two power transistors, one pulling up, one pulling down. They're switched to a fairly high frequency, so Class D amplifiers tend to have quite good efficiencies. And then there's some filtering on the output to remove the high frequency. Now, if we go back to the chip view, basically the top 2/3 of the chip is the power MOSFETs. Now, if I come down a little bit, you can see, of course, the lower third is going to be some amplifiers, and there's going to be some control logic as well. I think it's a dual-channel chip. We'll see that in a second here. So there are some identifying marks on the chip. One says chip star, I believe, but when you Google that, it doesn't seem to pull up too much in terms of vendors. But interestingly enough, if I start to delayer the chip, basically that means stripping metal off by layer. This is my first shot at trying to take the very top metal off and then stopping the process. Basically, the very top of the semiconductor will be a glass-like substance, and it's a passivation layer, and then there's going to be metal, and there should be another passivation below that. So, and here I'll just transition between the two photographs I have, where I took the first layer of the metal off, and actually this is kind of successful, more successful than I've been in previous attempts. Now, if I go to the third picture here, this is where I've stripped away the entire metal, and all that we're left with is the diffusion layer. Now, of course, clearly you can see that this was a dual-channel design. You see, of course, a sort of a symmetry left to right there. What else? Let's zoom in a bit to one of the sections that has a bunch of rectangles in a row. These are almost certainly digital logic gates. These are obviously quite large, and unlike the last teardown we did last week, this process node's so big it wouldn't be very difficult to measure the gate size here. Quite large, but of course that makes sense. This product being a power amplifier for audio purposes would not need a deep sub-micron or sub-nanometer process. You could get away with something very, very modest because you do need very large transistors to do a power function. Coming back to the diffusion layer photograph, although I said I stripped it down the diffusion layer, you can clearly see in the top section some of the metal remains. And if we zoom into that, you can see the construction of the chip a little bit clearer. You can see, of course, the diffusion layer they pointed out, the metal layer just above it, and then the very top metal layer, and perhaps even actually a third metal layer. So this might be a 3-metal process. So that's a very classic structure for a power FET below. Coming to the bottom of the chip, just circled in red are the some squares. I'm fairly certain those would be capacitors. You need some sort of filtering function in Class D amplifier, and I suspect that is contributing to the filtering function. So that was the teardown of an induction speaker with a Class D amplifier. As always, if you want to take a look at these silicon die shots, they're on my blog, electronupdate.blogspot.com.